check out fluid forces and momentum. We've got all of these formulas in A2, but now let's break it down. We've looked at a few up here already. Let's break it down a little bit further and take a look at these. First thing we want to look at is buoyancy force, which is our F sub B here. We get density and pressure along with it too, and these should be reviewed topics hopefully. If not, let's go over them quickly here. Density is rho, and pressure P are important to the understanding of the buoyancy force, and density is our mass per unit volume. So rho really is mass per unit volume, and the unit of density is kilograms per meter cubed. Pressure is the force per unit area, which is this graphic over here. You can see the force pushing down on this area. And so the SI unit then, of course, is newtons per meter squared. Or you can call it a Pascal, PA, where 1 newton per meter squared equals 1 Pascal. Pressure is a scalar quantity, and as fluids act in all directions, that pressure is going to act in all directions. So for solids, pressure acts in the same direction as weight. The pressure of the atmosphere acting at the surface of the Earth is about 100,000 newtons per meter squared, or 10 to the 5th power pascals. The other thing we're going to be looking at with buoyancy force now is upthrust. So this upthrust is what we're going to be calling our force upwards here. This is the buoyancy and the upthrust of it. So this buoyancy force can be calculated by rho v times g. So the rho is the density of the liquid, our v is the volume of the displaced liquid. That's this part of the liquid right here, displaced liquid. And the g is the acceleration due to gravity. And the buoyancy force arises from the pressure difference between the top and the bottom of the object. So we've got a pressure here and a pressure here, and it could be different, and that's really how it floats or doesn't float. The height of the object floating above the surface of the fluid depends on the relative densities of the fluid and the object. So when the densities are equal, the object has neutral buoyancy in the fluid. When the object's density is greater than the fluid's density, the net force is downwards and it sinks. So let's think about that for a moment. It's more dense than the surrounding fluid. Well, that makes sense that it goes down. When the object's density is less than the fluid's density, then the net force is going to be upward, so it's going to float. The volume that a floating object has displaced has the weight equal to the total weight of the object. So if you see something that has displaced a certain amount of water, well, that water has the same weight equal to the object that is now inside of it. So this leads to Archimedes' principle. And Archimedes' principle says that objects float, so the fraction of their volume that's below the water must be equal to the density of the object over the density of the fluid. And that's going to be the volume that is below the water. So they really have to equal 1 in that case. And here we've got some positively buoyant, some negatively buoyant, and neutrally buoyant. You can see it's not quite touching the bottom here. Let's take a moment to try a practice buoyancy question. Pause the video and come back in a moment. Well, the buoy of uniform cross-sectional area floats in water with 0.75 meters of the height submerged below the waterline. The density of the fresh water is 1,000 kilograms per meter cubed. Calculate the mass of the buoy, and then the buoy is now placed in seawater of greater density than fresh water. Explain the change, if any, in the submerged height. So is this going to change at all when it's now stuck in salt water? Well, the first one, Newton's first law, says that since the buoy floats without sinking, the buoyancy force must be equal to the weight of the buoy. So from Archimedes' principle then, this force is equal to the weight of the water that's displaced by the buoy. By combining the two laws, we can deduce that the mass of the buoy is the same as the mass as the displaced water. So calculate the mass of the buoy. So the mass of the water then is the same as the mass of the buoy. So the mass of the buoy is the same as the mass of the displaced water. So let's say our mass is the density of the water times the volume of the water. We've got our density times this is the height that's submerged below the line, and multiply it by the cross-sectional area. So we've got height, we've got width, and we've got density here. So that's going to be our volume. Our length times width is going to be our volume. And then we got meter squared here and meters, so that gives us meters cubed. That's going to be our volume. 150 grams in this case. For part B, a smaller volume is needed to displace the mass of the seawater equal to the mass of the buoy. So a smaller height of the buoy will be submerged and more of it will float above the water. Pretty cool. When we're talking about fluid resistance, we also need to talk about terminal velocity. So in this case, a skydiver is jumping out of a plane. There's initially only the force of gravity on the person. So after some time falling through the air, the drag force starts to grow. And here you can see the drag force starting to grow. It's not quite as long as the mg force yet. The drag force then pushes back on them. When the drag force and mg are balanced, then the skydiver stops accelerating, and that's called terminal velocity. Here we can see a graph. From your notes, if you would, pause the video and label these sections of your graph. We're really talking about the speed going up very fast here, and then you can see it slowing down to a constant speed. And then once the parachute opens, it slows way down until it's at a constant speed, but it's again a terminal speed, and then landing, bang. So the force of drag, we can say that we can apply this to moving vehicles, to sports, to falling objects, and wind tunnels are a useful study of drag. And in a wind tunnel, we have an object that's kept stationary where the speed of the air then that's flowing across it is varied. The drag of an object moving through air or liquid depends on many things, and it's got to be the object's size and shape, the nature of its surface, whether it's smooth or bumpy, its speed, and the nature of the fluid that's going across it. Is the fluid air? Is the fluid water? Is the fluid something much thicker or more viscous than that? Typically, for small objects moving slowly, the drag force is proportionate to the velocity, but for large objects, that drag force is proportionate to the velocity squared. So let's take a practice moment here. Pause the video. Let's read it through first. Calculate the upwards force acting on a skydiver of mass 80 kilograms who is falling at a constant speed. Now you can pause the video and come back for the answer. Well, the weight of the skydiver is going to be our mg, so we end up with 784 newtons. Because the skydiver is falling at a constant speed, that's the terminal speed, the upward drag force is equal to the downward weight, so therefore the upwards force has got to be equal to this, which is 780 newtons, to our significant figures of 2 here. You might even say 1. Would you say it's 800 or 780? Maybe say 784. I like all those answers. For viscosity and viscous drag, what we want to talk about is, what is this word viscosity? Well, when an object moves through a fluid, it has to push the fluid out of its path, and the fluid's resistance to such a movement is called viscosity. Clearly, the greater viscosity will tend to increase the drag force, which is called viscous drag. Some typical values at 20 degrees C are over here. We're talking about heavy oil or light oil or water. What's the viscosity here? Well, you can see our Greek letter here. The viscosities of some substances can be different at different temperatures, so some things could be more thick if they get cold. Let's now look at viscosity and how it fits with Stokes' law. For a simple situation where we have a smooth spherical object of radius r moving at a speed v, which is not enough to cause turbulence or that irregular movements in the fluid, what we can say is that under these circumstances, the viscosity is given by the symbol eta and has the SI unit of PAS, a poids. It's a French sort of pronunciation of this word, and it's kilograms over meters over seconds. And viscous drag formula is given by this, which is 6 pi eta times the radius times the velocity. And this is one of our data booklet references from A2. For Stokes' law and terminal velocity without mass, what we can do is we can say that both viscous drag and buoyancy need to be considered when an object moves through a fluid like this. So a sphere dropping under its own weight through a fluid is subject to weight, which is a downwards force, that's mg, the buoyancy force, which is upwards. We're going to remember that as rho vg, and we've got drag force, which is upwards, and we just looked at that one with Stokes' law. And when we sum all those forces, what we end up with is weight, which is downwards, my b, so we subtract b, the buoyancy force going upwards, and the drag force also going upwards. So we can say that we start with weight going down because it's going to be going down in this case. So let's see if we can get a positive value for this one. The mass can be replaced by the sphere's density, or rho, and the volume, so that we can end up with the net force being the density of the sphere times the volume times gravity minus the density of the fluid times volume times gravity minus Stokes' law here, which is our 6 pi eta, which is our viscosity, and then our radius times velocity at the end here. As the sphere falls, the total upwards force increases because of Stokes' law, means that the drag force is proportional to the speed, and that's the v over there. So eventually the sum of the buoyancy and drag will equal the weight downwards, and we're going to call this condition once again terminal speed. So if we set the net force to 0 and we arrange it, we end up with this terminal speed. We can call this the formula for terminal speed of an object in a fluid. So it's kind of a useful formula if we want to apply it. For terminal velocity with mass and the volume of the sphere, what we can do is we can say if a sphere is a mass m and a radius, and they're moving with constant terminal speed, then the upwards and downwards forces on it are going to be balanced. And so then the viscous drag and the force of drag plus the buoyancy force, and our buoyancy force is going to equal our weight. So what we end up with here is our Stokes' law plus our rho vg equals mv. And this is very much like what we just did. But what we can do now is we can add in the volume of a sphere. The volume of a sphere is going to be 4 on 3 pi r cubed. So what we can do now is use this volume and substitute in for the v's that you can see above. So we'll put our 4 on 3 pi r cubed right here. So we end up with Stokes' law plus our 4 on 3 rho g pi r cubed is equal to mg. So if the mass and the radius of the sphere are measured and the terminal speed being determined in this way, then the equation can be used to determine the value of the viscosity of the liquid. And this could be something that we could do in an experiment, assuming that the density of this is known. And that density would be the density rho here. Sounds like a good IB question for me. Let's try a practice question. 2 steel balls of mass m and 2m fall at constant speeds in a tube filled with oil. Which of the following correctly compares the magnitudes of the net force and the drag resistance force on the balls? Take a moment, pause it, and then come back for the answer. All right, let's think about this now. So we've got 2 balls that are falling through the fluid here, and they're both falling. And we're asking about the magnitudes of the net force and the drag resistance force on the ball. So the net force and the drag force, are they going to be the same or are they going to be different? Well, in this case, what we can think of is that the net forces on them are going to be the forces downwards and the forces upwards all added together. So for the net forces of them, it's going to need to be similar with both of these. So our terminal velocity has been reached, so the forces are going to be balanced. So therefore it's got to be either A or B in this case. And if the mass and shape of the larger ball will be different, therefore the drag force is going to be different. So what's the drag force going upwards on the large one compared to the small one? I'll bet you can guess. In that case, we're going to need to say that it's going to be different. Our answer is going to be B. All right, let's take a look at momentum. Here are some learning objectives for this section. We've got Newton's second law expressed in rate of change of momentum, impulse and force time graphs, conservation of linear momentum, as well as elastic, inelastic collisions, and explosions. Here are the formulae from our data booklet. We've looked at a few already. Let's focus on this one now and these three formulae. For momentum, you may remember that we have P equals mv, and our P is momentum, m is mass, v is velocity, and it's the measure of how hard it is to really bring an object to a stop. This is a data booklet reference from the second section. An object has more momentum if it has more mass and or more velocity in this case. Symbol of P, it is a vector quantity. It's calculated as mass times velocity. And we've got our units of kilograms times meters per second. It's a vector quantity. So when we have two cars that are sort of crossing paths like this, if we tilt this a little bit, we can see the top view of it. What we have here is the momentum of car A plus the momentum of car B, which is that upwards arrow there, where we end up with a vector sum of the two, that combined momentum. So if we look at an example problem of momentum, we could say a 100 kilogram player, the first one over here, moving at 5 meters per second, collides directly with another 75 kilogram player moving at 9 meters per second. Which way will they fall? Take a minute to see if you can check it out, and you can stare at this amazing drawing of stick figures here. Alright, hopefully you paused it and you checked it out. But what we want to do is to figure out what is the momentum of each one. For the first person, I'm getting about 500 kilogram meters per second. The second one, 675 kilograms per meter, kilograms times meters per second. The players are going to be falling to the left. The principle of linear conservation of momentum says that if no forces from the outside system act on the object in the system, then momentum is always conserved. So we're going back to that idea of forces. The conservation rule has never been known to be broken, and in cases of nuclear physics, it seemed like some conservation laws were being broken, but then scientists proposed that there were actual unknown particles acting that were yet undiscovered, and subsequently, of course, many of the particles were found to exist, and that it preserved the principle of linear conservation of momentum. We'll get into that a little bit more when we look at nuclear physics. So the next topic that we really want to look at, or next vocabulary term, I suppose, is impulse. And impulse is the change in momentum, and we can call it J in this case. This is another formula that we're going to look at here. So J equals force times delta T, and this is change in time. So if we apply a force to an object, and the speed and the momentum it gains or loses is not just on the force, but also on the time that the force is applied. So if you think about this, if you push something for a longer time, you're exerting more impulse on it, causing more change in momentum. So that impulse really is force times time. That's going to be the change in momentum. So what we can do then is start to look at a new way to look at Newton's second law. So Newton's second law says that the net forces are equal to mass times the acceleration. Of course, the acceleration is equal to force on mass. We can also say that the acceleration is equal to the change in velocity over the change in time, and we looked at that during kinematics. So what we can say is that these two can be set equal to each other. Then, of course, we can equate our F and T together. We can cross multiply F and T and delta V and M. And we can use this for changing masses, like when a rocket is moving and it's losing fuel as it's moving. We can actually use this for calculating the burning of a fuel as it moves and what's the momentum of it. We can also say that the net forces are equal to bringing that velocity over mass times change in velocity over time. So the F net is going to be our M times, of course this is A, right? Our delta V over delta T is A, so this is just F equals MA. And remember, the impulse is our mass times the change in velocity. We can also say it's the change in force times change in time. And remember that letter we're going to use is J. That's going to be change in momentum. Let's also go back and take a look at this formula right here and change that to look just like Newton, where we can say this M over V, this M times V is really going to be P, or delta P if this V is changing. We can call it delta P on the top. There's our delta T on the bottom, and we can also say this is equal to F and MA at the same time. So this is another data booklet reference that will stay with you wherever you go. Impulse is when momentum is not conserved, but we can change momentum with forces from outside the system. This force is from outside the system is always part of a force pair. So if it's a force pair, it's going to have another force with it. So if a car is driving and runs into a wall, could be a force pair or an outside force on this system. If the car puts a force on the wall will put a force on the car. This impulse happens very fast, so the force is very large. Here you can see velocity is large, and now we have a large force because it's a small time. We can also say that our J is equal to force times time, and the force is that delta P on delta T. An example could be that a truck is stopped by a pile of hay. Here you can see velocity is big. In this case, the time is very large, so the force is small. In this case, when the velocity is very big and time is small, we end up with the force on the truck being very large. Second example is a boxer that moves his head backwards. So that boxer is actually moving backwards, and when he gets hit, you notice he's still got that smile on his face, where I don't know if he's going to be smiling this much because his head is moving forward. The fist is also moving in the opposite direction. This is really going to cause some damage here. I don't think he's smiling anymore. Let's try a worked example here. A cart moves in a horizontal line with a constant speed v in meters per second. Rain starts to fall and the car fills with water at a rate of x kilograms per second. So it means every second x kilograms have fallen on the cart. The cart must keep moving at a constant speed. Determine the force that must be applied to the cart. So in this case, we have a cart and we need to keep it going at the same speed, but there's rain falling in it, and as it gets more and more mass, it starts to slow down if our P is conserved. So let's see how we're going to do this. Go ahead and try it. Pause the video and come on back in a moment. Alright, hopefully you've paused it and tried it. In this case, we usually would think that the force would be 0 since the cart's not accelerating, but we do need a force since the momentum of the cart is increasing, because the mass is increasing in this case. So the force is going to be our F net, that's our delta P on T. We can say our delta P is the change in momentum and velocity over T. And in this case, it's the change in mass. The velocity needs to stay the same. So what we can say is that it's the velocity times x. And our x is going to be the rate in kilograms. So what we can say is that F net is going to be that velocity times the rate of change here. So if we say the speed of the cart is 3.5 meters per second and the rate filling of the cart is 0.2, we could actually find our 0.7 newtons as our answer for the change. Determine the force that must be applied. Well, we have to keep applying this force. And interesting thing is we have to keep applying this force every second. So we increase the force every second as it's filling with water. Kind of a strange question, but a fun one. If we look at forces, again, we're talking all about forces in this unit. Let's look at the forces when we're talking about a car that's traveling down the road and runs into a mosquito. And answer the following questions based on the situation. Take a moment, see if you can answer these, and then come back and let's talk about them. Well, if we take a look at these questions now, hopefully you paused it for a moment and took a guess and checked it out. We're comparing the forces on them. Well, the forces are going to be equal and opposite in this one. That's going to be action and reaction. If we compare the time of the impact for the vehicle and the mosquito is going to be exactly the same. What about comparing the impulse of them? Well, we just compared the force and we just compared the time, so the impulse, or the J, is also going to be exactly the same. For comparing the change in momentum, well, the change in momentum is actually just the impulse, so that one is also going to be the same. But what about the accelerations and the damage? These are going to be a little bit different. The acceleration, the bug is going to have a larger one, as the idea is that it has a positive acceleration and then it has a negative acceleration. So the car is going to continue moving in the same direction it's going, and it is going to slow down a little bit, but the mosquito is going to have quite a large change in acceleration. What about the damage? Well, the damage in this case is going to be on the bug, or should I say the damage is going to be the bug on the car. Let's take a look at a ball hitting a bat in this case. The ball has an initial velocity u before the collision and a final velocity v. So here we have u about to strike it. What we're going to say is in the second situation here, where we actually put a force on it, we can get the ball to fly off. But we will first look at this situation. So the ball's acceleration, our average acceleration, is given by the final minus the initial over time. And with Newton's second law, this is the F net is equal to ma, we can say our acceleration is our final minus initial on time. So then we end up with a final equation here of mass times final velocity minus mass times initial velocity on time. Then finally, if we move the t over, we can have the sum of the forces times t is equal to final minus initial, mass times final velocity minus mass times initial velocity, set equal to impulse here. This could also be j. So what we really have here is that the product of force and time is impulse, which is the change in momentum here. So looking at bouncing or sticking, this is kind of an interesting situation with momentum. Determine the change of momentum and the impulse on the ball. The first situation, we've got no bounce, it sticks. This is going to be what we're calling an inelastic collision, where they stick together. Let's say the ball has an initial velocity of 3 meters per second and it sticks. The second situation we're going to look at is when it bounces off the wall, same mass, same initial velocity, but now it bounces off the wall and comes backwards towards us at 1 meter per second. Let's see if we can figure out determining the change of momentum on each of these situations. Pause it and then come back in a moment. Alright, hopefully you've paused it and tried it out. used some of the equations. What we're going to do for this first situation is say that the change in momentum is our mass times the final velocity minus the mass times the initial velocity. And that final velocity is going to be 0, so we end up with 1 times 0 minus 1 times 3. That gives us a negative 3 kilogram meters per second. So the impulse then is going to be negative 3. So the magnitude really is about 3 newtons a second, whether it's going to be to the left or to the right. In this case, it's going to be to the left as the wall stops it from moving to the right. The second situation, when we're talking about B with a bounce, we can say the same, that our mass times the final velocity minus mass times the initial velocity. In this case, we end up with 1 times minus 1 minus 1 times 3. So we end up with 4 kilogram meters per second. The impulse is actually larger in this case. In other words, the amount of force per time is going to be larger in the second case. So when things are bouncing, they have a larger impulse than when they're actually sticking. Newton originally thought that momentum was a quantity of motion, so he put it into his Newton 2. When v changes for an object, the acceleration is 0, therefore there is no change in momentum. Newton says the only way to get a change in velocity is to apply a force. The force is the average force applied over a time interval, which is our delta t. And if delta t is very small, our F is going to be very big, and vice versa. We can also look at a situation where things are bouncing. If one sticks and one bounces, we know the one that bounces is going to have a greater impulse. So the change in momentum is a vector. Since momentum is a vector, and objects that change 180 degrees usually have larger impulse. Let's look further into this. Try an example problem here. Pause it and come back. In this one, a ball of mass 200 grams traveling at 10 meters per second bounces off a wall. If, after hitting the wall, it travels at 5 meters per second, what's the impulse? Well, we've got our before, we've got our after here. I always like to draw a diagram. So we have an initial, we have a final. What we can say is that our F delta t is impulse. And so our impulse is going to be our mass times final minus initial. We can put our mass in there, final minus initial. Our final is going left, so we have a negative 5. And of course we have 10 here, so we end up with negative 3 kilogram meters per second. Let's do another one. Pause it and come back. If we calculate the impulse on a tennis racket that hits a ball of mass 67 grams traveling at 10 meters per second so that it comes off a racket at a velocity of 50 meters per second. So we're calculating the impulse. Pause it now if you haven't yet. Alright, let's try it now and see what we can come up with. We're sticking with our F times t being impulse. Our delta p is also impulse, and of course so is our mass times final minus initial velocity. Plugging in our numbers, we can get something like 4 or negative 4 kilogram meters per second. Let's try another one. Third example here. This one is about a baseball with a certain mass to it, 0.14 kilograms, has an initial velocity of u equals, and I think there's a minus sign there, minus 38 meters per second. It must be going left. As it approaches a bat, I think it is. The bat applies an average force that's much larger than the weight of the ball. And the ball departs from the bat with a final velocity of positive 58 meters per second. Determine the impulse applied to the ball by the bat. This is kind of a fun question. Pause it. Come on back in a moment. Alright, hopefully you've paused it. We're going to start off the same way we have before, plugging in our mass and our final velocity minus initial velocity to get our 13.4 kilogram meters per second. The second question now says, assuming that the time of the contact is this is 1.6 times 10 to the minus 3 seconds, find the average force exerted on the ball by the bat. Pause it and try this one. Well, average force now is going to be our force times time. So we have our impulse on time is going to equal force. Here's our impulse. Plug in our time. We can get our force in newtons. Pretty cool. The last one says, find the average force exerted by the bat on the ball. Well, if the average force exerted on the ball by the bat is this, well, then they have to be equal and opposite of each other. So the same force, but in the opposite direction. So it's going to be negative 8,375 newtons. Pretty cool. Here's an IB question. Let's check it out and see if you can do it. Pause the video and come back in a moment. Well, interestingly enough, this is the same situation as we've been looking at before. Our impulse here, it's looking for the change in momentum, which is impulse. And in this case, the given variables, positive u, is in the opposite direction. Notice it's going to the left. So one of the things that they're going to do here is they're going to keep our positive and negative conventions. So if something's going to the left, remember we have to give it a negative sign. So the way we can write this is we can say m times final velocity, which is going to the right, minus initial velocity. So we end up with A as our answer. Another example, example number 5. During a storm, rain comes straight down with a velocity of 15 meters per second and hits the roof of a car perpendicularly. The mass of the rain per second that strikes the roof is 0.060 kilograms per second. So this is how much mass per second is smashing into the roof. Assuming that the rain comes to rest upon striking the car, find the average force exerted by the rain on the roof. So when we say it comes to rest, it's not bouncing off the car, right? So this is going to be an inelastic collision. It's not going to turn around. The impulse is not going to be quite as much as if it was going to bounce. The impulse would be larger if it was bouncing. Take a minute to try it out, and let's look at the answer. If we consider that this amount of mass of rain and it has an impact every 1 second. Let's figure it out in this case, this kilograms of rain. So we have our impulse is equal to mass times velocity, which is equal to force times time. Our force is mass times velocity on time. We can plug in to find the force of 0.90 newtons every second. So find the average force exerted by the rain on the roof. Well, this is going to be 0.9 newtons every second. Let's take a look at part B now. In this case, we can say that part B says instead of rain, suppose hail is falling. And hail is a type of ice or a very solid precipitation that comes from clouds. The hail comes straight down as a mass at a mass rate of mass divided by time, 0.060 kilograms per second, so the same rate as we saw before, and an initial velocity of 15 meters per second, and bounces off the roof perpendicularly. I think the other one, we were looking at 15 meters per second too, so it's the same speed, same mass, but now we're talking about it bouncing, and it bounces off the roof perpendicularly. Would the force on the roof of the car be different than in part A? See if you can explain. Pause now and try it out. Well, in this case, the force is going to be bigger. We know because as it bounces, that delta P is going to be larger. the change in velocity is going to be greater. In other words, we have a positive and then we have a negative as it bounces. Secondly, the time is going to be smaller since it's bouncing too. So if we say our mass times velocity is going to be larger, our time is going to be smaller, that's going to result in a much bigger force. This is why hailstorms are so much more damaging than rain. I've had quite a few times of people that I know after a hailstorm actually have to have their roof on their house replaced. Let's look at another example. Example 6 says a 0.5 kilogram ball is dropped from rest above a hard floor. When it reaches the floor, its velocity, it has a velocity of 4.0 meters per second. The ball then bounces vertically upwards. A graph of the velocity against time for the ball is shown. So here we have the bounce. Find the magnitude of the momentum change of the ball during the bounce. And then part B says the ball stayed in contact with the floor for 0.15 seconds. What is the average force, or what average force did the floor exert on the ball? We're looking at forces again. Go ahead and pause it and come back for the answer. Well, in part A, we're looking to find the magnitude of the momentum change of the ball. So that momentum change, as we know before, is our mass times final minus initial velocity. So what we can say is right here in this spot, that's going to be our final minus initial velocities. So minus 2 is our final velocity. Positive 4 is our initial velocity. And so we end up with our 6 meters, or 6 times 0.5. In this case, it's because our mass is 0.5. So we can say our mass times this is going to be 3 kilogram meters per second. For part B then, if the ball stays in contact with the floor with this for this small amount of time right here, you can see it's stayed in contact with the floor that long. Well, we can do the same thing with our force, is mass times velocity on time, with our mass times the velocity of it over time, plugging in our masses, plugging in our time to get 20 newtons. Pretty cool. A similar analogy, a skateboarder is thrown a heavy ball. If you're catching a heavy ball like this, you'll notice what's going to happen. You can kind of imagine when the ball is caught by this person. Or if you're on a skateboard or something like this where it moves and you throw a ball this way, what's going to happen to this person? You can kind of see what's about to happen. Pretty cool. Now let's look at force and time graphs. So each of these graphs has force on the y-axis over here in newtons, and we have time on the x-axis. This is kind of a strange one, as we have the x-axis here in the middle. A constant force, a non-constant force, and a force that varies linearly over time. Which one is which? Well, in this case, we've got our constant force here. We've got a force that varies linearly over time. And here we have an impact. This is something that's actually bounced. It's gotten to a height of force, and then it starts to elongate it again. This could be like a ball bouncing off a wall. Let's take a moment to look at this situation where I have a tennis racket. Any tennis players out there? You know who you are. As the ball pushes in on this tennis racket, so here's our side view of a tennis racket here. You can say, yes, my tennis racket looks awesome. That's great. The force grows to a maximum, just like we were talking about. So if we look at the graph down here, we can see it increases to a maximum, and then it decreases again as the ball moves back out of the net. The question is, how much impulse is each square worth, and what's the total impulse exerted on the object? So we're looking for J here. How much is one of these squares worth? Well, let's take a look. Each box is 0.5 Newton seconds. So we've got 5 times 0.1, and so this whole area here is going to be 0.5 Newton seconds. And the interesting thing about Newton seconds is, remember, it's force and time together, so this really is the same as kilograms times meters per second. This is a unit of momentum. For the second part, where it says, what's the total impulse exerted on the object? Well, the total impulse is going to be the area under the curve. And what I've done is I've taken that area and multiply it by 0.5. I count about 4.5 squares. 4.5 squares times 0.5 is going to give us about 2.25 Newton seconds. The second part of momentum that we're going to start looking at now talks about the second law, the same idea of the second law, and I think these are the same objectives, aren't they? Let's look now at the law of conservation of momentum. We can recall that 1 Newton, if the force net is 0, that the V is constant. This is the first law of Newton's laws of motion. And this law extends Newton 1 to cover all sorts of systems. So if we have a system of 2 spheres here, they're going to bounce off of each other. We could consider the 2 balls a system, and the forces become internal forces, and they balance each other out. So in this system, the whole system here is balanced if we look at this as one system. So the law of conservation of momentum here, if the F net of the system and the momentum of the system then is going to be constant, the total momentum before the collision is equal to total momentum after the collision. So you can see our astronauts up here. One is simply floating, one is coming in pretty fast, and then they sort of move away a bit slowly. Well, that's because their mass got larger here. It also extends to the vector sum of these two. So if we look at situation A here, we have a ball that's rolling and one that's not. When they smack together, the darker ball is actually going to stop rolling. The white ball is going to take all of that energy, that kinetic energy away, that velocity, especially if their masses are the same. For B then, if they're both coming at each other, they could smack into each other, and that motion might translate as the darker ball giving its motion to the white ball, and the white ball giving its motion to the darker ball here. We can also see a situation like this, where one of the spheres is approaching faster than this one is going. Although this one has some rightwards velocity, it's less than this one. So this one catches up to it, smacks into it, and after it smacks into it, their velocities then switch. This velocity is the velocity from the white ball, and this velocity is the velocity from the darker ball. Cannons work the same way. If there's no motion before, well, the momentum of the cannon and the ball has to equal 0 if we're talking about the conservation of momentum. So the momentum of the cannon and the ball together have to equal 0. So what we can say is after the cannon fires a cannonball here, we can say that the negative momentum of the cannon and the positive momentum of the ball itself are going to be 0. Or in other words, the absolute values of each, the magnitudes are going to be the same. The big mass of the cannon moves at a small velocity backwards, and the small mass of the ball moves at a large velocity forwards. So this is how we get the ball to come out so fast. The cannon moves back just a little bit, but it's very heavy. Sometimes these cannons would also be built into the ground. So you would be looking at the mass of the earth and pushing back on the cannonball. Bombs work the same way. If we have shrapnel or pieces of a bomb that move off in different directions, well, we know that the momentum before is 0 if it's just sort of sitting there. Afterwards, the momentum has to be 0 too. We can take our vector components and line them up, and we'll notice we are back where we started. Let's try a test question here. Joe is standing on the surface of a frozen pond and he throws a ball horizontally. Considering Joe and the ball together, which one of the following correctly describes the change in the magnitude of the momentum and the change in the kinetic energy of Joe and the ball immediately after the ball is thrown? Take a moment to read over the answers, pause the video, and come back. Well, in this case, if we're talking about Joe and the ball together, they're going to have no change in momentum. So we're narrowing it down right now to A and C. And if we have no change in momentum, the kinetic energy of Joe and the ball definitely increases. When we talk about inelastic collisions, these are the sticky types of collisions. Inelastic collisions are where the objects now travel together. So something like this, where one object is moving, the other object is not moving, they smack together and then suddenly they move together with a velocity, a combined movement together. You notice it's proportionate as well. So elastic are when objects collide and bounce off of each other. We have no kinetic energy that's lost in this case, the momentum is conserved. Inelastic collisions are when objects collide and stick together. Some of the kinetic energy is lost, or it can be lost. The momentum is conserved. And when we have perfectly inelastic collisions, we end up with the maximum kinetic energy that's lost, and this is where they stick together. So still, in each case, our momentum is going to be conserved. If we have a ball that's bouncing like this, we can have a steel ball that's dropped on a hard floor. It comes back up almost to the same height because it is elastic, this elastic collision that's happening. It's lost no kinetic energy in the collision with the floor, or very little. If we have a soft or a partially deflated basketball that's dropped, it will not come close to the same height, which was dropped because it's lost most of that kinetic energy in the collision with the floor. As a third example we can look at with a completely deflated basketball where it literally just sticks to the floor, doesn't bounce at all. It's lost all of its kinetic energy in the collision with the floor. Let's do a few example problems together. Let's try an inelastic problem here. A moving cart with a mass of 800 kilograms has an inelastic collision with a stationary cart with a mass of 400 kilograms. Given the speeds, what is their final speed? Pause the video now and come back in a moment for the answer. Alright, hopefully you've paused the video. Let's take a look again at that conservation of momentum. Well, before we know the momentum of cart 1 is plus the momentum of cart 2, we can calculate that momentum, about 24,000 kilogram meters per second, and we know afterwards the momentum must be the same as well, 24,000 kilograms times meters per second, if they're stuck together. But now we have the momentum of the cart plus the momentum of cart 2 has to equal the mass of the first cart plus the mass of the second cart times the velocity. There should be a little plus in there. So what we end up with is 800 plus 400 times our velocity. Now we can solve for v. We end up finding our v, which is about 20 meters per second. Can you confirm that? You can also look at a practice problem like this where it says show that the final velocities of the blocks shown below are as indicated. In other words, in the beginning, the black mass has a speed of v, and when they combine together it has a speed of half v. Can we do that? Well, we can use our same formula here. The mass of the black block plus the mass and the velocity of the black block plus the mass and the velocity of the blue block before the collision, and the mass of the black block times the velocity of the black block after the collision plus the mass of the blue block times the velocity of the blue block after the collision. So we've got before and we've got after the collision here. Well, the second part here, when we're talking about the mass and the velocity of the blue block before the collision, what is its momentum? Well, because the blue block starts out with no velocity, this term turns to 0. So we're simply left with this first term and these last two terms. So we can say 2 times m times v prime. And what I've done is I've used v1 and v1 prime to show that this could be different, and v2 prime over here. Afterwards, the velocities might be different. So now we have our m1 v1 equals 2m v prime, and our m's cancel. So we end up with v1 is equal to 2 v prime, which gives us the v prime of v1 on 2. We've proven it. Let's take another look at conservation of momentum. Starting from rest, 2 hockey players push off of each other on a smooth, level ice. We've got some Detroit Red Wings here, where the friction is negligible. It's very slippery. Now, player 1 is less massive. Player 1 is 54 kilograms. Player 2 is more massive. He's 88. And player 2 moves away with a velocity of 2.5 meters per second. Find the recoil velocity of player 1. Pause the video and try it out. Well, in this case, we'll simply do the same thing. Set up our momentum before is equal to our momentum afterwards with different velocities over here. The first two terms are where they are not moving. So in fact, they're starting from rest. So we've got these two terms actually go away or turn to 0. So what we can say then is we can move our m2 v2 over to the other side. By subtracting it, we can subtract m2 v2 to get our m1 v1 prime is equal to negative m2 v2 prime. They're going to be going in opposite directions with each other. We're really looking for the velocity of 1. So let's plug, we can algebraically solve for v1 prime. That's this one over here, the speed of player 1, and we can plug in our negative m2, the mass of m2, the speed of our second player, and the mass of the first player to get our final velocity. Can you confirm that value? Let's try a practice question here. Another test question. 2 spheres of mass m and m2 are moving towards each other along a same straight line with speeds v1 and v2 as shown. The spheres collide. Which of the following gives the total change in linear momentum of the spheres as a result of the collision? Pause the video, and remember, 1 is A, 2 is B, 3 is C, 4 is D, and 5, well, you know what 5 is. Let's take a look at the idea of this question. It's asking for the total momentum change in the system. And since it's a collision, the momentum is going to be constant or conserved in this case. Let's try another one. Read over the question, pause the video, and come back for the answer. Well, in this case, when we're talking about these 2 spheres, the word magnitude means that we're looking at scalar quantities of them. So this is kind of an interesting question. We need to add the sign to our vector quantities. So when we say whether they're going right or left, we really need to put in those vector quantities now. So in the beginning, we end up with px is going to the right, so it's positive, py is negative, and in the second case, we end up with px is positive and py is also positive. So we end up with B as our answer, ending up with our px minus py is equal to px plus py. Let's try one more. Two objects undergo an inelastic collision. Which of the following is correct in respect to both the conservation of momentum and the conservation of total energy of the system? Take a moment to try it out and come back for the answer. Hopefully you tried the problem out. The first thing that we want to talk about is that the momentum is conserved in all these collisions. So we've narrowed it down now to A or B. The second thing we want to talk about is that inelastic means that the kinetic energy is not going to be constant. So we end up with A. I hope this was helpful. At the very end here, please do complete those momentum video practice questions as well as your practice momentum test questions.